Hey everyone, and welcome. Today, we are diving deep into the invisible world of waves. We're going to witness a showdown between two totally fundamental ways that energy moves through our universe. Let's jump right in. So, have you ever stopped to think about this? Seriously, a ripple in a pond is this visible up and down thing, but the sound coming from your speaker, that's just a vibration in the air you can't even see. On the surface, they seem like they have nothing in common. Well, it turns out, physics says they're family. And we're about to find out how. Okay, here's our game plan. First, we gotta lay down the rules and figure out what a wave even is. Then, we'll meet our two big contenders, the up and down wave and the push and pull wave. After that, it's the main event, the showdown. And finally, we'll see why this whole thing actually matters in our everyday world. First things first. Before we throw these waves into the ring, we need to understand what we're even talking about. So, what on earth is a wave? Okay, here's the absolute key takeaway. A wave is all about moving energy, not moving stuff. Think about doing the wave at a stadium. People stand up and sit down. They're just moving in their spot. But that wave of energy travels all the way around the stadium. Nobody's actually running from one end to the other. That's the big idea. It's energy on the move. All right, it's time to meet contender number one. This is the one you probably picture when someone says the word wave. That classic, beautiful up and down motion. Let's meet the transverse wave. And this is its signature move. The little particles that make up the medium, say water molecules, they move up and down. But the energy of the wave, that's moving forward, side to side. They move at a right angle to each other. It's like they're making a T-shape, perpendicular. That's the key word here. So let's look at the stats for this wave. Its highest points are called crests, and its lowest points are called troughs. You've seen this a million times with ripples on a pond. Now here's something really interesting. For mechanical waves, the kind that need a medium, transverse waves usually only travel through solids. Why? Well, think about it. For a particle to pull its neighbor up, they have to be pretty tightly connected, right? You can't really do that in a liquid or a gas. And now for our second contender. And this one is a totally different kind of beast. This wave doesn't do the whole up and down thing. Nope, this one moves by pushing and pulling. Say hello to the longitudinal wave. See the huge difference? With this one, the particles vibrate back and forth in the exact same direction or parallel to the way the energy is traveling. It's less of a graceful dance and more of a forward and back shuffle. Okay, checking out the stats for this one. Instead of crests and troughs, it's got compressions, where all the particles are bunched up tight, and rarefactions, where they're all spread out. The absolute perfect example is sound. And check out its medium. This wave is not picky at all. Because all it needs to do is bump into the particle in front of it. It can travel through solids, liquids, and gases, no problem. All right, we've met our two contenders. We know their styles, we know their signature moves. It's time for the main event. Let's put them head to head and see how they really stack up in the ultimate showdown. This right here breaks it all down perfectly. Look at that very first row. Particle motion. Perpendicular versus parallel. Honestly, that one single difference is the reason for everything else on this chart. Because of it, you get crests and troughs on one side and compressions and rarefactions on the other. It's why one is picky about its medium and the other can travel through anything. And of course, the heavyweight champions for each type, light versus sound. So, we've seen all the physics, we've had the showdown, but you might be asking, why should I care? Well, in this last part, we're going to see how this isn't just textbook stuff. These two types of waves literally build the world you and I experience every single day. Take a look at this number. 300,000 kilometers per second. That's just an insane speed. Any guesses what travels this fast? Yup, it's the speed of light, the universe's ultimate speed limit. Light is our champion transverse wave, but it's a special kind. It's an electromagnetic wave. And this is the exception to that solids-only rule we talked about. It's so special, it doesn't need any medium. It can just zip right through the total emptiness of space. It's the whole reason we can see the sun and the stars. Now let's switch over to our longitudinal champion, sound. What you're seeing here is pretty wild. Sound actually travels about 4 times faster in water than it does in air. And the reason is simple, really. The particles in water are way more packed together than they are in air. So that back and forth push gets passed along way more efficiently. It's a perfect example of how the medium is everything for a longitudinal wave. And this brings it all the way home, right into our own bodies. Our ability to hear. It's all thanks to longitudinal waves. Your eardrum is basically a super sensitive detector for tiny changes in air pressure. And what are those pressure changes? They're the compressions and rarefactions of a sound wave. Our entire sense of hearing is built on this push and pull physics. So there you have it. From the light that hits your eyes to the sound that enters your ears, our whole reality is basically painted by these two types of waves. It really makes you wonder, doesn't it? If our entire world is built on these invisible rules of energy, what else is out there that we just haven't learned to see yet? What other cool phenomena are waiting to be discovered?